started looking at alkyl condensations, and we said, you need a base that will remove some of the alpha hydrogens, but not all of them. So something like sodium hydroxide, sodium methoxide is good, but a much stronger base like enbutyl lithium would not be good, because that would remove 100%, give you 100% of the enolate ion, and then this reaction would not be possible because we need a mixture of the aldehyde or ketone and its enolate ion, so that the enolate ion can act as a nucleophile and attack the electrophilic carbonyl carbon, form this bond, join these two pieces together, and then it may or may not happen. You may need to force it to happen. Sometimes it happens naturally, or without you having to do anything else, that this is going to dehydrate and end up forming this double bond and alpha beta etc. So that would be a typical alkyl product. So do the same, but show me the alkyl product now from two cyclopentanones reacting together. Okay, so what you're going to have to do, this is your electrophile here. I need to make my nucleophile, and that's going to be the one where you'll remove the alpha hydrogen and put 2 electrons there. This is then going to go ahead and attack the carbonyl. This is going to pick up a hydrogen. So we're going to have, let's say, OH here, and then forming this carbon-carbon bond to this ketone. This would be your initial product. It might or not dehydrate. If it does dehydrate, then the product you're going to end up with is going to be this one. right? It's this hydrogen next to the carbonyl, which is pretty acidic, and that is going to be removed with this OH to form this carbon-carbon double bond.
You can also put H2SO4 with heat, right? Instead of the minus H2O, like that dehydration.
Sulfuric acid is going to give you an enol, and your enol is not nearly as nucleophilic as an enolate ion, because your enol is going to be something like that. Yes, this could attack, but this is inherently a much weaker nucleophile than an enolate ion. I'd rather form an enolate ion. So typically you have base in there.
We always need to equivalence of our stuff.
How are you going to put them together? I mean, I don't need to write two equivalents. You understand that if I write this molecule, I have a pot and there's millions and millions of them. But I'm just trying to kind of let you know, there's two of them reacting together. So that's why I put two equivalents. Now, whether you're looking at the beta hydroxyketone or the alpha beta unsaturated ketone, the bond that you made is the one in red. So, if we're going the opposite direction, that is, if I give you the product and I ask you, what is this being formed from? This is the bond that in your head you're going to break. And the piece that has the carbonyl, the carbon double bond oxygen, that's the original piece. The other one lost the oxygen because it dehydrated or it became an OH. But this is inherently what will tell you what your original molecule was. Okay, so you just need to recognize, again in here, in your head you would break this, and the piece that has the carbonyl is what your original molecule used to look like. In this carbon, this hydrogen is the original molecule. Okay, so that would be the way to do a retrosynthetic analysis, see what the, which original aldehyde or ketone this is coming from. Now, this and this with the beta hydroxy aldehyde and then dehydration of the beta unsaturated ketone or aldehyde. The fact that we need not a very strong base but a weaker base. And we can dehydrate the alcohol that we formed. And we get 28. Now, it is possible to try to condense two different aldehydes, or an aldehyde and a ketone, but usually that results in a horrendous mess, because it can condense with itself and the other one. And so, under those conditions, you typically end up with a mess. Unless one of the two pieces cannot form an enolate ion. It doesn't have an alpha hydrogen. And then there's only one that can form an inner link ion, and the other one has to be electrophile. So for example, if you have benzaldehyde, there is no alpha hydrogen here that can form an inner link ion. There is no hydrogen there, period. So the only one that could form an inner link ion would be this, and this could attack in here, and it would be reasonably clean. Let's just not even consider cross-arrow condensations. Let's just ignore those and only give you things that I made from this thing. Okay, but the possibility exists. So ignore this. Now, it is possible to have aldehyde and ketone on the same molecule. And if you have 3 or 4 carbons in between, then if one becomes a nucleophile, the other one electrophile, that would result in forming a ring. So for example, if you have this molecule on the left, and you extracted the hydrogen here, that is your nucleophile that attacks this electrophilic carbon, forms this 5-membered ring, and then I would lose hydrogen OH and form a double bond right here. So that would be an intramolecular. Now, let's ask a couple of questions. Why didn't I choose to either remove this hydrogen or this hydrogen? And it would be possible, but why am I only showing cyclization like this? What would happen if we formed this? It would attack here, right? And that would give me a 3-membered ring, which is incredibly strained. The rings that you're going to form are 5 or 6-membered rings. Much smaller or much larger than that is unlikely to form. So if there's an option between forming a 5 and forming a 3, trust me, the 5 is going to form exclusively. Okay. So really, this is the only reasonable one that will give you a 5-membered ring. Now, there's lots and lots of molecules, commercially important molecules, that contain this form of cyclohexenone, with various groups over here, lots of perfumes and things. So this would be a kind of interesting way of synthesizing that. Start from the open chain and then cyclize it, and you've got everything in the position you wanted, and so on and so forth. But again, this is an intramolecular alkyl. So let's look at this and show me the product that forms when this is treated with some base sodium hydroxide. And I gave you a perfectly symmetrical one, so it doesn't matter which one you enolize, you're going to get the same one. Okay, so it doesn't matter whether I form the enolate ion here or here or here or here, you'll end up with the same product. This attacks here, this bit of a hydrogen. Now, on the right-hand side, we're going to have a 5-membered ring, where, let's say, this one is my OH. And on the left-hand side, we're going to have 1, 2, 3, 4, 5, 6, 7. So, let's say 1, 2, 3, 4, 5, 6, 7. And this is where, this is where my ketone is. So that would be your beta hydroxy ketone. Now, if I were to eliminate, where's the double bond going to end up at? And then between the two rings, right? Because remember, it's the hydrogen next to the carbonyl that is your most acidic hydrogen being eliminated with this OH. So you're going to end up with a double bond here. If it dehydrates. Oh, no, it's not dehydration. It could.
Can you show how you counted the carbons again to make the blue side?
How? Oh, how do we count it?
Yeah, like I don't know.
So there is basically a bond here and you form OH. So this one on the right has 1, 2, 3, 4, 5 sides, or 5 carbons. And this one on the left has 1, 2, 3, 4, 5, 6, 7 carbons or sides. So this is the alpha carbon, alpha to the carbonyl, beta carbon, alpha carbon, beta carbon to the carbonyl. That is the bond that was formed. So retrosynthetically, that would be the bond that you would break in your head. Okay, so let's do that. Let's look at some molecules and tell me what the starting material was. So what is that molecule coming from? And what is that molecule coming from? So remember, focus on the carbonyl. The carbon next to the carbonyl is the alpha, this is the beta, this is the bond that was formed. The piece with the carbonyl is the original molecule. And we just put two of these. This just happens to be this, right? It's basically pentanal that added to itself and gave me that after dehydration. Butanol. And this is coming from this. You can sort of think about this piece and this piece, but both of them are 3-pentanol. So 3-pentanol adding to itself in an Aldol reaction. So obviously this is the aldehyde precursor, and this is the ketone precursor. Okay.
So if the double bond isn't there next to the carbonyl, it's obvious that it wasn't dehydrated, right?
Well, you're going to see an OH on carbon number on the beta carbon, right? This would have been this without the dehydration. But you're still looking at the bond between the alpha and beta carbons. And the piece with the carbonyl is still the original molecule. Okay? So, the only thing we have left is, well, what if we use a stronger base? What if we make 100% of the enolate ion? Then the aldol is not a possibility. Now, one very common strong base that we're going to use is if you start with diisopropylamide, and you put N-butyl lithium. This base abstracts this hydrogen, and you make this lithium salt, lithium diisopropylamine, that has this very, very basic nitrogen. Also a large base, a very large, strong base. LDA is used almost exclusively in this reaction. So you are going to come with a strong base, abstract one of these alpha hydrogens, and make 100% of this enolate ion. Whether you draw it like that, or you draw it like this, right? But you have 100% of this. So it's not going to be adding to itself. An alkyl is not possible, but it can now add to, let's say, an alkyl halide and do an SN2 type reaction. So this is going to be a way to add substituents alpha to the carbonyl. Okay, so put LDA, make the anion, attach something like ethyl bromide, and now you formed this over here. Because the base is so large, if there's an option between alkylating at a more hindered or less hindered position, the less hindered position is the preferred one. Now, you're trying to put one equivalent of the base, because if you put too much more, you still have all kinds of acidic hydrogens here that you could remove, and you could end up polyalkylating. But presumably you can regulate and just add one alkyl. Okay, so let's do a couple of those, and then we're done with this chapter. So only one of these reactions will work. Which one will work and why? Because it's an SN2 reaction. And to do an SN2 reaction, we need an alkyl halide. We need a bromine or halogen connected to an sp3 carbon, preferably methyl or primary, or secondary, not tertiary, not an sp2 carbon, nothing like that. Both of these are going to form the enolate ion. That's not the problem. The problem is then this needs to go and attack from the back and displace this. But we're not going to do this, right? Because this is not a methyl primary or secondary alkyl halide. So SN2 is not possible. And only this one will happen. And the last one, this is going to be a intramolecular alkylation. So show me what the product would be. solvent and ether solvent tetrahydrofuran, don't worry about that. In this case, I blocked this side, so you can't even make the enolate ion there, but even if you could, the chances of this closing on forming a four-membered ring when you could possibly form a six, you're going to form the six. But the base abstracts the hydrogen alpha to the carbonyl, you form your enolate ion, SN2 reaction, and you're going to end up with a six-membered ring. Okay. So, we're going to move to chapter 20, which is a chapter on carboxylic acids. As usual, the first thing we do is deal with some naming and properties. Like aldehydes, now let's remember aldehydes. So the IUPAC name of this will look at the fact that you have 4 carbons and an aldehyde and call this butanol. The IUPAC name of this is going to look at the fact that you have 4 carbons and call this butanoic acid. You have, the common name of this, remember for 1 carbon, the prefix for common names was form, like formaldehyde, and 2 carbons, acet, and 3 carbons, propyl, and 4 carbons, butyl, butyraldehyde, propionaldehyde, whatever. So the common name for this would be butyraldehyde. And remember, you would then, these would not be numbered, but you would use your Greek letters. And starting from the carbon next to the carbonyl, this would be alpha, beta, gamma, delta, whatever. So you happen to have, let's say, a methyl group here, then this would be 2-methyl butanol, and this would be alpha methyl butyraldehyde. And this would be 2-methyl butanoic acid or alpha methyl butyric acid. you're going to have formic acid, acetic acid, propionic acid, butyric acid. Okay. Very similar. I don't need to tell you that the carboxylic acid is on carbon number 1, just like I don't need to tell you that the aldehyde is on carbon number 1. There's nowhere else where it can be. Now, if you happen to have 2 carboxylic acids, there's going to be one in one end and the other one in the other end. And then it would be like a dioic acid or something like that. Now, carboxylic acids are, of course, big surprise, acids. So they are weak acids. This is your acidic hydrogen. And your water could abstract this hydrogen and put a negative charge here. This is your carboxylate ion. The carboxylate ion is, you can write resonance structure for it. Again, a pKa of 5 means this is a weak acid. It's not HCl with a -2. It's not, but certainly stronger than water or something like that. This group COOH, you can see it written like this. You may see it written like this. You may see it written like this. But you always recognize that as a carboxylic acid. In water ionizes, about 5%. So we still have significant amounts of this, but small amounts, 5% or so of the carboxylate ion. Okay, now, if you hear something like a fatty acid would be the carboxylic acid, but then with a very long hydrocarbon chain, 10 to 20 carbons, that would be a typical fatty acid. All right. So again, Greek letters, this would be gamma amino butyric acid. When you go to health food stores, you can buy GABA. It's supposed to calm you down. Alpha chloropropionic acid. IUPAC names, of course, are numbered. 2-chlorobutanoic acid. In this case, we're calling this trans because we're looking at the double bond. This is carbon number 1, this is carbon number 2, this is carbon number 3. There's nothing that has a higher priority than a carboxylic acid. The carboxylic acid carbon will always be 1 no matter what else is attached. Unless you have 2 carboxylic acids and then one is going to be 1 and the other one is going to be whatever else. Okay. So this is effectively a 3-carbon propenoic acid, because it's not propanoic because it's a double bond. 2-propenoic acid because my double bond is between carbons 2 and the next higher carbon. So this piece is this, right? But then we call it trans because the 2 hydrogens are trans, and on carbon number 3 we have this phenyl group attached. So we call it trans 3-phenyl 2-propenoic acid. So remember that we would talk about like a cyclopentane carbaldehyde, something like that. This cannot be part of the ring like a ketone, that would be cyclopentanone. Aldehydes, carboxylic acids must be outside. So we call this like a cycloalkane and then carboxylic acid. So this would be like a cyclopentane carboxylic acid. That will talk about that. But then I will need to name this substitute, right? So we assume when we say cyclopentane carboxylic acid that the carboxylic acid is on carbon number 1, and therefore this would be on carbon number 2, 2-isopropyl propylcyclopentane carboxylic acid. This here would be the parent name. Aromatic carboxylic acid is benzoic acid. This would be ortho-hydroxybenzoic acid, or there's an even more common name, salicylic acid. Dicarboxylic acids are at the end. So let's say this is carbon number 1, 2, 3, 4, 5, 6, or alpha, beta, gamma, whatever. So I could call this 3-bromohexane dioic acid. 6 carbons, 2 carboxylic acids. Now the common names for dioic acids have all kinds of weird names. Oxalic, malonic, succinic, glutaric, anthritic, blah, blah, blah. I'm not going to test you on these, but if you do biochemistry and you're looking at your TCA cycle, whatever, all of them are going to be there. We call them pretty much exclusively by the common name. But I will always be using the IUPAC name in dioic acids. Okay, so let's look. First, draw these compounds. So cyclobutane, dicarboxylic acid on carbons 1 and 2, and those two are trends. So one in front, one on the back. So this is indicating 2 double bonds. One between carbons 9 and 10, the other one between 12 and 13. Octadeca means 18 carbons total, 2 double bonds, and a carboxylic acid in carbon number 1. So let's say you have a carboxylic acid on carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a Z double bond of 6, 10, 11, 12, another double bond, 12, 13, 14, 15, 16, 17, 18. This would be a typical unsaturated fatty acid. And then benzoic acid is this. And this is orthohydroxybenzoic acid. Now, I'm not going to ask you again the common names. So let's go through that. So adipic acid would be this right here. So we're talking about 4 CH2s in the middle and 2 carboxylic acids, a total of 6 carbons. So we have a carboxylic acid, 1, 2, 3, 4, and a carboxylic acid. That would be a adipic acid. This is carbon number, this is alpha, this is beta. So on the beta carbon, we have the same group. Butyric acid, you know what it is. It's a 4 carbon carboxylic acid. On the alpha carbon, we have a methyl group. Fumaric acid is this trans molecule, and then it tells me that I have 2,3-dimethyl. So that would be that. So how would you call A, the IUPAC name? Yes, so first is substituent. So 3 amino, and then hexane dioic acid.
So you don't have the number where the carboxylic acids are?
They can only be at the ends. It's a given. there's only one, it's on carbon number 1. If there's 2, one is on carbon number 1 and the other one is the other. What do you call B? 2-methyl butanol, yes. What do you call it? Yeah, you need to start either trans or E to E, whatever you prefer. So you say 2-3, and then 2,3 dimethyl. And you would say, it's unnecessary to give the position of a double bond because there only be one place, and let's give it 2-butene dioic acid. But again, this, where else are you going to put the double bond is not, if not between carbons 2 and 3. Again, you could have called this trans in this particular case as well. Alright, so that's a little bit of the naming. This carbon is, of course, trigonoplanar, sp2 hybridized, flat. You have resonance here. The oxygen, the carbon and the oxygen are trigonoplanar and flat. So think about having this pure orbitals and lateral overlap and these electrons being delocalized. While we draw it with a double bond and an oxygen here, remember this resonance, and so both of these oxygens have, a fair amount of negative charge, and then they interact with this positive hydrogen over here. So that interaction between a reasonably negative oxygen and a positive hydrogen is hydrogen bonding, and carboxylic acids can hydrogen bond on both ends, and so they form very, very stable dimers like that, which of course give them very high melting points and boiling points because it takes a lot of energy to react at one point. So the typical carboxylic acid, like acetic acid, it only has 2 carbons, but it boils at 118 degrees Celsius, and that's because of the hydrogen bonding. Fatty acids. So if your fatty acid has carbon single bonds only, we call it a saturated fatty acid. And it's the type of fatty acid that typically makes fats, solids at room temperature. Whereas your oils, your liquids at room temperature, tend to have 1 or more cis double bonds. What these cis double bonds give is like a kink. It's more rigid. So while these guys all kind of clump together and give a very dense little ball, those rigid structures keep those chains apart. So the volume they occupy is larger. And remember, density is mass over volume. So If you make the volume larger because of the kinks of the double bond, your density is going to go down, which means it tends to be liquids at room temperature. So double bonds, vegetable source, oils and fatty acids, and liquids at room temperature. The more double bonds you have, the lower the density, the lower the melting point. So for example, a fully saturated 16 carbon fatty acid melts at 69 degrees, right? I would need to really heat it to get it to melt. Oleic acid from olive oil with one system of bond. It's a liquid because it melts below room temperature. And linoleic acid with two system of bonds is now will be a liquid in the freezer. Okay. The only remotely water-soluble part of a carboxylic acid is this end. If you have, this kind of hydrogen bond to water all over the place. So this end is hydrophilic. But as I start adding more and more hydrocarbons here, this tail is going to be non-polar and hydrophobic. So small up to 4 carbons are reasonably miscible in water, soluble in water, but get them much larger and they will become really fatty and greasy and not dissolve in water. Why, if both of these, an alcohol and a carboxylic acid, have an OH, why is an acid and an alcohol not an acid? How do we judge the strength of an acid?
Strength of the conjugate base.
By the stability of the conjugate base. My conjugate base here is resonance stabilized. It's a lot more stable than having all the negative charge stuck on one oxygen. So that means that my alcohol has a pKa of 16 to 18, while this is a pKa of 5. This is like 10 to 12 million times stronger acid because of the resonance. Now, how acidic this is varies with the stability of the conjugate base. If I put electron withdrawing group, remember that the conjugate base has a negative charge. Anything that takes away electron density is going to make that more stable. So electronegative groups that at least inductively through the sigma bonds can kind of remove some electron density, it's going to make this more stable, which makes the acid a stronger acid, which means a lower pKa. So we're going from 4.74, put one chlorine, 2.86, put a second chlorine, 1.26, put a third chlorine, we're down to a pKa of 0.64, which is pretty much a strong acid. Okay. And here, if I had electron donors, and I put negative charge here, this is not going to want to have a negative charge. So this is going to be less acidic. Whereas if I have an electron withdrawing group that takes electrons away, having this positive charge is going to make this more acidic, easier to come up. So this is 4.46, this is 3.41, whatever. Okay. So the acidity changes a little bit based on your substituents. So let's look at problem 3. So we're comparing hydrogen, bromine, fluorine. Everything else is the same. Which would be the most acidic?
Bromine. Fluorine.
Which is a more electronegative atom? Fluorine. So this is taking electron density away more strongly, and hydrogen the least. This is the most acidic. This is the least acidic. Now on the bottom, we're looking at different functional groups. OH, amino group, carboxylic acid. Which is my stronger acid? The carboxylic acid, without question. What will come next? Yeah, this has to do with electronegativity. Oxygen and nitrogen are about the same size, but which is going to be happier with a negative charge, the more electronegative atom. And therefore, this is more stable, which means the acid is a stronger acid. Amino groups are bases. They're not acids, they're bases. Okay? They pick up hydrogen to become positively charged, kind of like ammonia. That is about as non-acidic as you can get. If you look at the actual pKa values, this would be about 33 or something, this would be 16, 17. This is going to be fine. You know, huge differences in pKa values. All right, so there's a whole bunch of reactions of carboxylic acids. First and foremost is the fact that they're acids and they react with bases. So, if you have a carboxylic acid and you put a base, the base and the acid are going to react together to form water. And the other two pieces, which are now, of course, charged, are going to form a salt. This is typical neutralization reaction. And so you can form salt of carboxylic acid. If this were, I don't know, acetic acid, this would be the acetate ion. The way that you write the ions of carboxylic acids, you change the NH acid for ATE. And this is a sodium salt, so you would call this sodium acetate, right? Salts, you always name the metal first, like sodium chloride, sodium acetate, that will be the name of that compound. All right, so salts are common. So this would be its easiest to name the carboxylic acid first, and then modify. We're going to see this is a strategy we're going to use to name salts, to name esters, to name amides, acid chlorides. I don't care what it is. They are all derived from carboxylic acids. So name the carboxylic acid first, and then change a couple of things. So your carboxylic acid here, if we ignore this, this is carbon number 1, 2, 3, 4, 5. So the IUPAC name would be what? 3-chloro-pentanolic acid. Right, so we're going to change the ending to ATE, pentanoate, and put, there's a potassium, now that we go back, put potassium. this had been an ester, we would call it, if this was a methyl group over here, but on potassium, we would call this methyl trichloropentanate. You know, and of course, if you have the common name, then this would be beta-chloro valeric valerate or something like that, if I've heard of it. So, those would be your iocaptan common names. Now, when you have a salt, that of course becomes quite water soluble. So, one of the things you do, your typical fat, so your typical fat is something where you have a 3-carbon backbone from something called glycerol, and then you have 3 carboxylic acids, fatty acids, you know, 20 carbons, whatever long. And then you're going to do what we call a condensation reaction, which is we're going to lose OH and hydrogen and form an ester bond, and lose OH and hydrogen and form an ester bond, and lose OH and hydrogen and form an ester bond. This is your typical triglyceride or fat or oil. It is fully saturated, chances are it's a fat, single bonds only, some double bonds, it would be an oil. Now, if we cook this with, let's say, sodium hydroxide, then your hydroxide ions are going to come, break this bond, blah, 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 and you're effectively going to form the salt of the carboxylic acids. So, because you're under basic conditions, you know, yes, we're going to get the glycerol back, or glycerin, but rather than forming the carboxylic acid, because we're still under basic conditions, we're going to form the salt of the carboxylic acid. 3 of them. Right, 1, 2, 3. This, right here, is right. This right here is soap. When you cook various fats and oils in sodium hydroxide, you form soap. And soap is a molecule that has an ionic head and a hydrophobic tail. Right. Ionic, hydrophilic, likes water, and something that doesn't like water. So when you have some grease on your shirt and it doesn't want to come off, and you put some soap, grease is nonpolar, the nonpolar tails of the soap molecules surround the grease, because nonpolar dissolves in nonpolar, while the ionic heads are going to interact with the water. So you form this little capsule, and now we can carry the grease in that little capsule. Okay. So that's one important application of salts. Many others, but certainly soap is a top contender, and that is how or Wednesday, you're sure, or you must let me know by Monday that you need to take it in the testing center. I'm going to start being really, if you have a work issue, if you have a class in all 3 of those times, then you can take it in the testing center, not because it happens to be convenient. So if you have a conflict with work on every day, or a conflict with a class on every day, then let me know, and I'll put a copy in the testing center. But you need to let me know by Monday. Okay? So I'll see you next week.